All right, in this video, we're going to talk about section 3.11, dealing with related rates. This will wrap up chapter 3 in the text. And basically, we're going to be solving problems that are dealing with related rates using some of the formulas in geometry, by the way. So pretty much this whole thing will be talking about just related rates, just taking derivatives with respect to time. All right, so here we're going to just return to the theme of derivatives as rates of change in problems in which the variables change with respect to time. And the essential feature of these problems is that two or more variables which are related in a known way are themselves changing in time. And I have a couple of examples here, like an oil rig springs a leak and the oil spreads in a roughly circular patch along the rig. If the radius of the oil patch increases at a known rate, how fast is the area of the patch changing? That is a related rate problem. Another one would be where you have two airliners approach an airport with known speeds, one flying west and one flying north. How fast does the distance between the airliners change? That can too be a problem where related rates are used here, okay? So here we're going to be determining the rate of change of one of the variables at a specific moment in time, okay? So this whole section, this whole video will be on related rates. And here's the procedure for solving related rate problems. And by the way, these are going to be word problems, so pretty much we're going to have to find the bits and pieces of information, identify those, and that will help us come up with our formulas that we're going to be using, and we'll take the derivatives of those with respect to time and solve them. All right, first of all, you want to read the problem carefully and make a sketch to organize the given information, okay? Read it carefully, find the bits and pieces, make a sketch if necessary. Also identify the rates that are given and the rate that is to be determined. Number two, you want to write one or more equations that express the basic relationships among the variables. And then number three is to introduce rates of change by differentiating the appropriate equation with respect to time t. Okay, because you're going to always take the derivative of both sides of the equation with respect to time. And then number four, substitute the known values and solve the desired quantity. And then number five, you want to check that the units are consistent and the answer is reasonable. Like, does the answer have the correct sign? Because sometimes you might come up with a rate that could be either positive or it could be negative. So you want to make sure that you do have the correct sign and that your units are going to be consistent with what you're looking for. So let's start with this first example. In this case here, the sides of a square increase in length at a rate of 4 meters per second. And here we got parts A, B, and C. At what rate is the area of the square changing when the sides are 16 meters long? And at what rate is the area of the square changing when the sides are 30 meters long? And then part C, you want to draw a graph of how the rate of change of the area varies with the side length. Probably one good way is go ahead and draw a figure of that of the square, which is what I'll do right here. Okay, it's just a sketch of a square. And of course, In a square, we have a side and a side. And now let's answer part A, where it says here, write an equation relating the area of the square, which is A, and the side length of the square, which is S. Well, the area of a square, if you recall back in geometry, of course, that would be A is equal to the side square. And in this case, since a rectangle is a square is a rectangle, I should say, an area of a rectangle is always going to be length times the width. So it'll be side times side in this case, or side square. So here's my formula. A is equal to S squared. And then the other part of part A will be to differentiate both sides of the equation with respect to t. Well, in this case, if your A is going to be S squared, the area of the square, then we take the derivative on each side of this equation with respect to time. So the derivative of A would just be dA dt. That's equal to the derivative of S squared with respect to time. Well, for the derivative of S squared, we have to bring down the 2, copy over the S to the 1 less power. So the S to the 1 is just S, but it's got to be taken with respect to time. So it has to be ds dt. So here you got 2 dA dt is equal to 2S times ds dt. Okay, so that's that part of part A. And then they're asking for at what rate is the area of the square changing when the sides are 16 meters long? Well, we know that S is 16 meters. That's the length of the side. So using this right here, dA dt is equal to 2 ds dt. We can find that out by just doing the substitution. We're finding the rate that the area of the square is changing. So dA dt would have to be 2 times S, which is 16, times ds dt. Well, here's what ds dt. Here's the problem. The side of a square increase in length at a rate of 4 meters per second. That right there is what ds dt is. Because the sides of the square increase at a length of 4 meters per second. Okay, so that's ds dt. So I've already got 2 times S, which is 16, times ds dt. That's going to be that 4 meters per second. And then I just go ahead and multiply this out. And by the way, this 16 is 16 meters. The 4 is meters per second. 2 times 16 is 32. 32 times 4 would be 128. And here, meters times meters is square meters, and then per second. So in this case, the area of the square is going to be changing at a rate of 128 square meters per second. And that's when the sides are 16 meters long. Now in the homework, they're going to have you fill in the correct answer, but then they want you to provide the correct units. For this one, you have to select the one that says meters square per second, because area is in square meters and the time that we're dealing with is in seconds. So the rate has to be in meters square per second. Okay, so all of that was part A. Now part B, the area of the square is changing at a rate of how many units when the sides are 30 meters long. So I'm going to do part B down here. The sides are 30 meters long, so that's your S, 30 meters. And I'm going to rewrite what dA dt is. Because dA dt is 2S times ds dt. And what that means here is this. This will be 2 times S, which is 30 meters. dsdt was given to us as 4 meters per second. So if I multiply 2 times 30, that will be 60. 60 times 4 will be 240. And then meters times the meters will be square meters per second. So that means that the area of the square is changing at a rate of 240 meters square or square meters per second when the sides are 30 meters long. And then in part C, which of the following graphs shows how the rate of change of the area varies with the side length? Well, it was 2s for dA dt, 2s ds dt for the derivative of a with respect to t. All right, so I'm going to put that 2s in the calculator, and then we're going to do the graph. But I'm going to treat that s like x. So let me go to include this. I'll go to y equal to, clear this out. And in this case here, in y1, I will put, it will be 2s, but I'm going to use x for that. Now, by looking at these graphs that I'm given here, here's what I'm going to do. I'm going to go to my window, press the window key. Notice on the vertical, on the horizontal axis is from 0 to 10, 0 to 50. So my x min would be 0, x max would be 50. And each of these marks here looks like they're in increments of 5. So that x scale will be 5. And then for the vertical axis, that's the y, that's from 0 to 200. So y min will be 0, y max will be 200. And the y scale, it looks like it's in increments of 20. So the y scale will be 20. Okay, and then I'm gonna press the button that says graph. And I'm gonna pick the graph that's close to the one that I have here based on those window settings that I put. And in this case, that choice would have to be answer B. So I'm picking that graph as the graph that best fits the rate of change of the area varying with the side length. Okay, so that's how we do one of those related rate problems here. Okay, let's look at another one, example 2. The area of a circle increases at a rate of 2 square centimeters per second. 2 square centimeters per second. And in part A, how fast is the radius changing when the radius is 3 centimeters, and how fast is the radius changing when the circumference is 3 centimeters? Okay. Now you're probably wondering about these formulas here. I've also included this in the handout as well. The geometry formulas here, this is on Canvas as well. So this will be a big help for you to pretty much be familiar with these formulas, especially for geometric figures, especially the ones for the 3-dimensional ones, because most of these will be used to help you do these related rate problems here. Okay. And you'll find this on Canvas as well. All right, so let's first see what we have here. The area of the circle increases at a rate of 2 square centimeters per second. That is the change in area with respect to time, dA dt. That's equal to 2 square centimeters per second. So at least we have identified something here. All right, so now let's answer part A. Write an equation relating the area of a circle A and the radius of the circle R. Well, if we go back to this sheet right here that I have here, here's the circle, and here's the formula for the area of the circle. That's pi r squared. So the area is equal to pi times the radius squared. Okay. So there's your equation of that circle. Next, we're going to differentiate both sides of the equation with respect to t. Okay, so in this case, if a is equal to pi r squared, and if I take the derivative on both sides of this equation, I'm going to have dA dt, and that's equal to, now pi is a constant, keep that in mind, so we bring that down, and then the derivative of r squared with respect to time. We bring down the 2, copy the r over to the one that's out. So it'll be r to the first, or just r, and then that's multiplied by dr dt. So this will be 2 pi r times dr dt. So that's the answer for that, for differentiating both sides of the equation with respect to time. Okay, and then they ask when the radius is 3 centimeters, the radius is changing at a rate of what? Okay. Now we know this, that dA dt is 2 square centimeters per second. We know that. Now I just bring this down. Now dA dt is 2 centimeters squared per second. So here I'm going to have 2, and that's equal to 2 pi r. And the radius is 3 centimeters. That's given to us. So we know that r is equal to 3. Radius is 3, that's given in part A, times dr dt. So we're finding dr dt in this case. Now, if I do 2 pi times 3, that will be 6 pi. So b 2 is equal to 6 pi times dr dt. And then divide both sides by 6 pi. So that means that dr dt is equal to, now, if I reduce 2 over 6, 2 goes into itself 1 time, 2 goes into 6, 3 times. So this will be 1 over 3 pi. And this will have to be in centimeters per second. Because the radius is in centimeters, the time is in seconds. And the rate has to be in centimeters per second. So when the radius is 3 centimeters, the radius is changing at a rate of 1 over 3 pi centimeters per second. And with that, you'll be given a drop-down menu to select your answers. Okay, now part B says, when the circumference is 3 centimeters, the radius is changing at a rate of what? Now, we're given that the circumference is 3 centimeters. So now we have to use the formula for finding the circumference of any circle. Now, if we go back to this handout, for our circle, the circumference there is 2 pi r. That's 2 pi times the radius. So we have to use c is equal to 2 pi r. And the circumference is 3 centimeters. That means capital C is equal to 3. Now I'm going to substitute the c with that 3, and that's equal to 2 pi times the radius. Now we need to solve for r, which is our radius here. It's multiplied by 2 pi, so I'm going to divide both sides by 2 pi. So that means r is equal to 3 over 2 pi. And that's, of course, in centimeters as well, because the radius is in centimeters, circumference is in centimeters as well. Now we're going to use that dA dt. That's equal to 2 pi r times dr dt that we found in part A. I'll bring that down here. That's dA dt, which is equal to this. Okay, so now, so here we're finding how fast is the radius changing when the circumference is 3 centimeters. Well, the radius is 3 over 2 pi, so let's substitute here. dA dt was 2 square centimeters per second. So in this case here, I'm going to bring down the 2, and I'm going to write in the units so that way you'll see how these units are dividing out. That's equal to 2 pi times the radius is 3 over 2 pi centimeters times dr dt. dr dt is what we're looking for here. Now, if I simplify this a bit, these 2 pi's divide out. So here I'm going to have 2 square centimeters per second, and that's equal to 3 centimeters times dr dt. And now to get dr dt by itself, I need to divide both sides by 3 centimeters. In this case here, those 3 centimeters divide out here. Now, if I divide the centimeters with a centimeter square, I'm going to be left with a centimeter in the numerator. So my final answer there for dr dt would be 2/3 centimeters per second. So when the circumference is 3 centimeters, the radius is changing at a rate of 2/3 centimeters per second. Again, a drop-down menu will be provided there as well. All right, so that's example 2. All right, example 3 looks like this. I need to bring this down a bit. It says here, it says that the edges of a cube increase at a rate of 2 centimeters per second. And how fast is the volume changing when the length of each edge is 30 centimeters? Okay, so let's draw a figure of a cube. So it's just a 3-dimensional figure, just like a square, but it's in 3 dimensions. Okay. So that's what a cube looks like. And we're going to write an equation relating the volume of a cube, which is V, at the edge of a cube labeled as A. So in a cube, all of your edges are equal in measure. And of course, the volume of any rectangular prism or rectangular box is always going to be length times the width times the height. So that volume is going to be A times A times A, which is in this case, A to the 3rd. So the volume there is A cube. Then we'll differentiate both sides of the equation with respect to t, or respect to time. So if v is equal to a cube, then the derivative on both sides. This will be dv dt. That's equal to the derivative of a cubed with respect to time would be 3a squared times dA dt. So we got the dv dt, and that's equal to, we'll just fill in the 3a squared, and then it's times dA dt. All right, so here we can go ahead and find out how fast is the volume changing when the length of each edge is 30 centimeters. So actually, we're finding out what dv dt is, because we're trying to find out how fast is that volume changing. We're looking for the rate that the volume is changing with respect to time. And the length of that edge, which is A, is 30 centimeters. Okay, so we're going to use this and then just substitute our numbers in. So dv dt is this. We got 3 times A, which is 30 centimeters, and that's squared, times, let's see, the edge of the cube increases at a rate of 2 centimeters per second. That means that's your dA dt. Okay. So dA dt is 2 centimeters per second. So dA dt, we replace that with 2 centimeters per second. And then we can find out what dV dt is going to be. Let's see, if I square the 30, that would be 900. 900 times the 3 in front will be 2,700. 2,700 times 2 will be 5,400. And this is centimeters squared times another centimeter would be centimeters cubed per second. So the volume, the rate of change of that volume is going to be 5,400. And it's going to be in cubic meters per cubic centimeters per second. Okay. Okay. All right, now example 4 on the next page. A circle has an initial radius of 50 feet. When the radius begins decreasing at a rate of 5 feet per minute, what is the rate in the change of area at the instant that the radius is 10 feet? Okay, so let's identify what we have here. The radius begins to decrease at a rate of 5 feet per minute. So that would be dr dt. The change in your radius with respect to time. And it's decreasing at 5 feet per minute. So it has to be negative 5 feet per minute. That's what dr dt is going to be, negative 5 feet per minute. Here it's important that you use the appropriate sign for this one. Because if it was increasing, it would just be positive. But here, since it's decreasing, 5 feet per minute has to be negative. And also, we want to find the rate in the change of the area at the instant that the radius is 10 feet. So our R is going to be the 10 feet. It won't be the 50 feet. All right, so now we want to write an equation of the area of the circle and the radius of the circle, which is R. Okay, so here's our circle. The radius, the area of the circle is pi times the radius square. So here's our formula. A is equal to pi R squared. All right, and now we want to differentiate both sides of the equation. So if A is going to be pi r squared, we differentiate both sides with respect to time. So it would be dA dt equaling to, bring the 2 in front of that pi, times copy over the r to the 1 less power, 2 pi r. And then we have to include that dr dt as well, because that radius is going to be, we'll take the derivative of that with respect to time. So that means dA dt is going to be equal to 2 pi r times dr dt. Okay. So now we can find the rate of change of area at the instant that the radius is 10 feet. Okay, so dA dt is what we're looking for. So dA dt is equal to 2 pi times the radius, which is 10 feet, times dr dt was negative 5 feet per minute. Okay. So dA dt would be, let's see, 2 times 10 is 20 times negative 5 will be negative 100. Bring over the pi, so it'll be negative 100 pi. Well, feet times feet is square feet per minute. So the rate of change of the area would be negative 100 pi, and that will be in square feet per minute. And of course, in the drop-down menu, you have to select the appropriate unit rate. Okay. All right, now let's look at example 5 on the next page. The volume of a cube decreases at a rate of 0.6 cubic feet per minute. What is the rate of change of the side length when the side lengths are 7 feet? Okay, so in this case, we're told the volume is decreasing at a rate. So that's dV dt. If it's decreasing, that means it's got to be negative. And the rate that they're dealing with is 0.6 cubic feet per minute. Okay. And when the side lengths are 7 feet, that's your S, which is 7. And we're looking for, in this case, the rate of change of the side length. That's, in this case, ds dt. That's what we're looking for here. Now, we first got to write an equation relating the volume of the cube and an edge of the cube, which is S. And of course, we can draw the cube, if you remember, as this was done in one of the previous examples. Length, width, and height are the same. So this will be S times S times S, which is S cubed. So the volume would be equal to S cubed. And that's written in terms of S. Okay. So now let's differentiate both sides of this equation with respect to time. Okay, and I'm going to do this down here. If the volume is S cubed, if I differentiate both sides of the equation, the left side would be dV dt is equal to the derivative of S cubed would be 3S squared times ds dt. So I put 3S squared there. Just fill that in as I would if I was doing this in my math lab. So this is my equation, differentiated with respect to time. Okay, so now let's simplify. dV dt is negative 0.6 cubic feet per minute. So I'm going to go ahead and write in that negative 0.6. Now I'll write in the units. And that's equal to 3 times S, which is the side length. That's 7 feet. And I should put feet here. So it'll be 7 feet. And that's going to be squared times ds dt, which is what I'm trying to find. And then next, I'm going to simplify the right side. I'll bring down that negative 0.6 cubic feet per minute. And that's equal to 7 squared will be 7 times 7 is 49. 49 times the 3 in front would be 147 square feet times ds dt. Now I need to solve for ds dt. That's being multiplied by 147 square feet, so I need to divide both sides by 147 square feet. So I'll have ds dt by itself, and that's equal to, now when I simplify these units, 2 of the feet will be gone. I'll be left with a foot in the numerator. And then if I divide negative 0.6 by 147, that would be my decimal value. But let's say they want this to 5 decimal places as needed. It says round to 5 decimal places. In this case here, this will be 0.00408. That 8 is the 5th digit after the decimal point. To the right of it is 1. So the 8 remains the same. So ds dt would be negative 0.00408. And this is going to be in feet per minute. So the rate of change of the side length when the side lengths are 7 feet is negative 0.00408 just in feet per minute. Okay. All right, example 6. A spherical balloon is inflating with helium at a rate of 64 pi cubic feet per minute. How fast is the balloon's radius increasing at the instant the radius is 2 feet? So now we want to write an equation relating the volume of a sphere, which is V, and the radius of the sphere, which is R. Okay, let's find that formula for finding the volume of a sphere. Okay, here's the sphere right here, and you're told what the volume is down here. V is equal to 4/3 pi times the radius cube. So V is equal to 4/3 pi times the radius cube. Okay. And I probably didn't write down what we have given right here. Let's see here. It's inflating, the sphere is inflating at a rate of 64 pi cubic feet per minute. That would be dV dt, because that's the volume. And I can tell because it has cubic feet. So that has to be volume. Usually volume is going to be in some cubic unit. So it'll be 64 pi cubic feet per minute. And how fast is the balloon's radius increasing at a rate at the instant the radius is 2 feet, well, that's your radius. R is going to be 2 feet. So we're trying to find dr dt, because we want to know how fast is that radius of the balloon increasing. Okay, now let's differentiate both sides of the equation with respect to time. So in this case, since our volume, and I'll do this down here, since I have space, the volume is the 4/3 pi r cube. And we want to differentiate both sides of this equation. So the derivative of v will be dv dt. That's equal to, and I'm going to bring down the 4/3. The derivative of r cube, I'm going to bring the 3 down in front of the pi, copy the r down to the 1 less power. And then if I simplify this, those 3's divide out. I'm going to have dv dt. That's equal to 4 pi times the radius square. And that's going to be, and I forgot something here, dr dt. I cannot forget that, because both of the variables have to be differentiated with respect to time. Okay. Now let's go ahead and simplify what just substitute what we already know. dv dt is 64 pi cubic feet per minute. This time I'll leave the units off. I'll just say 64 pi. And it's equal to 4 pi times the radius, in this case, it's going to be 2 feet. So this will be 2 square. And we're looking for dr dt. Dr dt has to be a unit in feet per minute. I will tell you that right now, because the radius is in feet. The unit of time is in minutes, feet per minute. Let's simplify the right side. I got 64 pi, and that's equal to 2 squared, or 2 times 2 will be 4 times this 4 in front will be 16 pi times dr dt. And then to get dr dt by itself, I need to divide both sides by 16 pi. So I'll have dr dt on this side. On the left side, the pi's divide out. 64 divided by 16 will give me 4. So this will be 4, and this will be in feet per minute as the final answer. Because again, the radius is in feet, the unit of time that we're dealing with is in minutes. So as a rate, it's going to be in feet per minute. So the balloon's radius is increasing at a rate of 4 feet per minute. There we go. 4 feet per minute. Okay, let's look at example 7. It says here a piston is seated at the top of a cylindrical chamber with radius 2 centimeters when it starts moving into the chamber at a constant speed of 2 centimeters per second. What is the rate of change of the volume of the cylinder when the piston is 15 centimeters from the base of the chamber? All right, now here we have a illustration of just that. Here's the piston right here, and that radius of that piston is 2 centimeters. Okay. So now that radius is going to be 2 centimeters because that's just the radius of the piston. That's not going to change. And of course, our height That's when the piston is 15 centimeters from the base of the chamber. Here's the base of the chamber right here. That height is 15 centimeters. Height goes up and down. Okay, and it's seated at the top, and it starts moving into the chamber at a constant speed of 2 centimeters per second. If it's moving in, that means that the height is going to be decreasing. Okay, the height decreases when we're moving this in, as you can see by these arrows here. The height is going to drop, it's going to decrease. So that means our change in height with respect to time has to be negative. So dh dt is going to be negative 2 centimeters per second. So here we're looking for the rate of change in the volume of that cylinder. So we're looking for dV dt. Okay. Now in this case here, they want us to let V, R, and H be the volume, radius, and height of the cylinder respectively. Write an equation relating V, R, and H. Well, this is a cylindrical chamber, so that means it's got to be in the form of a cylinder. So we need to find out what the formula is for the volume of a right circular cylinder. And in this case, the volume of that right circular cylinder will be V is equal to pi times the square of the radius times the height. Okay, so that's our formula for the volume of a right circular cylinder. V is equal to pi times the radius squared times the height. Now we're going to differentiate both sides of this equation with respect to time. So the derivative of V would be dV dt is equal to, now, I want you to know something here. I'm not going to differentiate the R. The reason for that is that this R is not going to change. That's the radius of this piston. It will not change at all because it's just going to go, what the piston is going to do is just going to go in. That will the radius there will never change. It's just going to remain constant. So I'm going to bring down pi r squared and only take the derivative of H with respect to time. And that is dH dt. Okay. Now, the only reason why I did not take the derivative of r squared is because this radius is not changing on this piston. It's just going, the piston is going in, but the radius will still remain 2 centimeters, no matter what. That radius is not going to change. So my dV dt will be equal to pi r squared times dH dt. Okay, now we're going to use this to find out what is the rate of change of the volume of the cylinder when the piston is 15 centimeters from the base of the chamber. Okay, so our height is 15 centimeters. In this case, the radius is 2 centimeters. But here, I just go ahead and bring this down. It's dH dt. All right, so in this case here, my dV dt is what I'm trying to find. That's equal to pi times the radius was 2 centimeters. And that's squared, times dH dt. dH dt was negative 2 centimeters per second. So here, if I simplify this dv dt, and you know what I'll go ahead and do? I'll put in the units, so that way you'll see that it's going to be in the appropriate units that we need here. The R is 2, and that's going to be centimeters. That's square. dH dt was -2 centimeters per second. So 2 squared is 2 times 2, that's 4. 4 times -2 would be -8, and bring down the pi. So it'll be -8 pi times centimeters squared times another centimeter will be centimeters cube per second. So dv dt is going to be -8 pi cubic centimeters per second. And here they want this to the nearest 100 as needed. So let's use our calculator and do this. -8 times, now there is a button that says pi right above the hat key. Right above the hat key is the Greek letter pi. So if I do second and hat for the pi, and then hit enter, to 2 decimal places, that would be -25.13. And this is in cubic centimeters per second. So when the piston is 15 centimeters from the base of the chamber, the volume of the cylinder is changing at a rate of about, and in this case, -25.13 centimeters, well, cubic centimeters per second. Questions on, well, if you have any questions, you can always send me an email or contact me if you have questions. All right, here's another example. As you can see, these examples are getting more difficult as we go along here. It says here, a 13-foot ladder is leaning against a vertical wall. When Jack begins pulling the foot of the ladder away from the wall at a rate of 0.4 feet per second, how fast is the top of the ladder sliding down the wall when the foot of the ladder is 12 feet away from the wall? Okay, so let's look at what we got here. So, and we're to let x be the distance from the foot of the ladder to the wall, and let y be the distance from the top of the ladder to the ground. And we're going to write an equation relating x and y. So here's the illustration that we have here. The 13-foot ladder is here. Okay, and we're told when Jack begins pulling the foot of that ladder away from the wall at this rate of 4 feet per second. And here we're letting x be the distance from the foot of that ladder to the wall. And it's going this way. And our y is going to be the distance from the top of the ladder to the ground. And notice when he's pulling it from the wall, the top of the ladder is decreasing. That means that y would be decreasing. So I know the y value is going to end up, or the change in y is going to end up being negative. Okay. So now, if this is 13 feet here, and we're trying to find how fast is the top of the ladder sliding down that wall, when the foot of this ladder is 12 feet from the wall, here's the wall, here's the foot, x is going to be 12. Now notice that this forms a right triangle, as you can see. This situation here forms a right triangle. So I'm going to be using something called the Pythagorean Theorem. And the Pythagorean Theorem is this. a squared plus the b squared will be equal to c squared. So here I'm using the Pythagorean theorem for this situation. A squared plus b squared is equal to c squared. And if I let x be the distance from the foot of the ladder to the wall, that's what a is going to be, x squared. Plus, I let y be the distance from the top of the ladder to the ground. That's this right here. That's going to be y squared, equaling to the length of that ladder, which is 13 feet. And that 13 will be squared. And if I square the 13, I'm going to get 169. So this will be x squared plus y squared is equal to 169. That's the equation relating x and y. X squared plus y squared is equal to 169. Now, if I differentiate both sides of this equation with respect to time, here's what I'm going to have. Differentiate or take the derivative of x squared, that would be 2x times dx dt, plus the derivative of y squared would be 2y times dy dt. That's equal to the derivative of 169, or the derivative of a constant, is 0. Okay. So I'm going to have 2x with the dx dt plus 2y with the dy dt. That's equal to 0 because the derivative of a constant is 0. Okay. Now, to answer when the foot of the ladder is 12 feet from the wall, the top of the ladder is sliding down the wall at a rate of what? Well, let's do this. That x squared plus y squared is equal to 169. I need to know something else. I need to know what y is. So let's use that to find out what y is. Our x is 12. So this will be 12, and that's squared, plus the y is what we're trying to find. So that'd be y squared is equal to 169. So now 12 squared is 144 plus y squared is equal to 169. And then to get y squared by itself, I'll subtract 144 on both sides. So that means that y squared is equal to 25. Then if I take the square root on both sides, and I'm only going to be dealing with positive measurements here. So I don't need the plus or minus symbol here. So y then will be equal to 5. So y is equal to 5. So here, this height right here at 12, when x is 12, that height there will be 5. Okay. So let me go ahead and gather up what I already know here. Because now I know that that Jack begins to pull the foot of the ladder away from the wall at the rate of 4 feet per second. So if this is pulling at a rate of 4 feet per second, that's going to be dx dt, because here's x right here, which is 12. So dx dt will have to be 0.4 feet per second. Okay. And I already know what x is. That's going to be 12. And I know what y is. That's going to be the 5. And I already differentiated both sides of the equation with respect to time, which was 2x dx dt plus 2y dy dt. That's equal to 0. Now let's go ahead and do some substitution here. All right, so here we're going to have 2 times x, which is 12. Dx dt is 0.4 plus 2 times y, which is 5. Here I'm trying to find dy dt because we're trying to find how fast is the top of this ladder sliding down when the foot of the ladder is 12 feet from the wall. So dy dt is what we're looking for. Then that's equal to 0. Now 2 times 12, that's 24. 24 times 0.4 will be 9.6 plus 2 times 5, which is 10 times dy dt. That's equal to 0. And now to get dy dt by itself, I need to first subtract 9.6 on both sides of this equation. So that means I'm going to have 10 dy dt is equal to negative 9.6. And then divide both sides by 10. Dy dt ends up being 9.6 negative 9.6 divided by 10 would be negative 0.96. And this is going to be in feet per second. So in this case here, when the foot of the ladder is 12 feet from the wall, the top of the ladder is sliding down the wall at a rate of negative 0.96, and this is in feet per second. And that would be true. That would make sense because if the ladder, the top of the ladder is going in the downward direction, that means that the speed is going to be negative. Okay. Okay, here's another example. Example 9. And that's this. Sand falls from an overhead bin and accumulates in a conical pile with a radius that is always 4 times its height. Suppose the height of the pile increases at a rate of 2 centimeters per second when the pile is 15 centimeters high. At what rate is the sand leaving the bin at that instant? And here we want to let V and H be the volume and height of the cone, respectively. Write an equation that relates V and H and does not include the radius of the cone. Okay. So we need to know what the volume, the formula for finding the volume of any right circular cone. Here it is. The volume in this case is going to be 1/3 pi times the radius squared times the height. So here the volume is equal to 1/3 pi times the radius squared times the height. But we got to write it in a way so it does not include the radius of the cone. Well, the piece of information that's going to help us is this. The radius, well, the conical pile will have a radius that is always 4 times its height. Well, R is the radius. 4 times the height would be 4 times h. So here the radius is going to be 4 times the height. So if I take that and substitute it for R in this formula for the volume of that right circular cylinder, here's what I have. V is equal to 1/3 times pi times, substitute the R with the 4h, so it'll be 4h, that would be squared times h. Oops. Now let's simplify this a bit. 1/3 pi times 4 squared would be 16. H would be squared times the h. Well, if I do 1/3 times 16, that's 16/3 times pi. H squared times h would be h cubed. So the volume in terms of just h and not including the radius of that cone will be this. V is equal to 16/3 pi times h cubed. Volume is equal to 16/3 pi times h cubed. And now we're going to differentiate both sides of the equation with respect to time. So dv dt, that's the derivative of v with respect to time. I'm going to bring down the 16/3 pi since it's a constant. The derivative of h cubed with respect to time would be 3h squared times dh dt. So now when I simplify this, the 3's divide out. That will mean dv dt is equal to 16 pi h squared dh dt. Okay, so now let's identify what we already have and then just substitute in this equation. Okay, we're told that the height of the pile increases at a rate of 2 centimeters per second. So that's dh dt right there. Height is changing at a rate of 2 centimeters per second. And it's going to be positive since it's increasing. And that is when the pile is 15 centimeters high. That's your height, 15 centimeters. Now we can find the rate that the sand is leaving the bin at that instant. That's a change in the volume, dv dt. So dv dt would be 16 pi times the height, which is 15 centimeters, times dh dt. Dh dt was 2 centimeters per second. Now I left something out here. This 15 centimeters should be squared because it's h squared and the height is 15. So it should be 15 centimeters, and that's going to be squared. Okay, so what I'm going to do here is, I'll show this on the calculator. 16 times 15, and that's got to be squared, so I use x squared, times 2. That would be 7,200. Now I'm going to bring over the pi. Centimeters squared times another centimeters will be centimeters cubed per second. And they're telling us to give us the exact answer using pi as needed. So here the sand is leaving the bin at a rate of 7,200 pi. And this is going to be in cubic centimeters per second. Okay. Okay, now example 10. Okay, looks like this. An inverted conical water tank with a height of 18 feet and a radius of 9 feet is drained through a hole in the vertex at a rate of 3 cubic feet per second, as indicated here. What is the rate of change of the water depth when the water depth is 5 feet? And they give you a hint. You have to use similar triangles here. Okay. Let's start by identifying what we have here. Notice here we have a cone, conical water tank. The radius is 9 feet. The height is in this case is 18 feet. But I don't think we're going to need that 18 feet here. I mean, yeah, because the height there is 18 feet. But here, they want us to find the rate of change of the water depth when the water depth is 5 feet at that instant. So that 5 feet would be your H. Okay. Okay. That 18 feet represents the height of the entire tank. But here we want the water depth, the change in the water depth when it's 5 feet. Okay. Now, we're also told something else. It's being drained through a hole at the vertex at a rate of 3 cubic feet per second. If it's drained, that means we're losing water. So that means that dV dt has to be negative 3 cubic feet per second. Why is it negative? Because we're draining this out. That means that the amount of the water is decreasing. The volume of that water will be decreasing. So that means that the change in the volume with respect to time, the change in water with respect to time is going to be negative 3 cubic feet per second. And they want the rate of change in the water depth, how deep, the height, dH dt is what we're looking for. Okay. First of all, we need the volume of a cone. And we already did this before with the volume of the cone. That's 1/3 pi times the radius squared times the height. Okay. I know what the height is. The problem with that is I know nothing about the radius here. I know nothing about that radius here. So this is where those similar triangles come in. Okay. So now I'm going to start with this big triangle right here that I have right here. I'm outlining this right here. And I can also go and do that in red. Okay. So somewhere down here, I'm going to give you that big triangle. Which was 9 feet. Going this way, the height was 18 feet coming this way. And now the other similar triangle is going to be right here where I have the height of the water. And I'm going to outline that in green. So here's that other triangle, which I'm going to draw down here. Okay. I know nothing about the radius here, so that's R. And I know nothing about the height. So that's R and that's H. So here's how I write my similar triangles here. And the reason why I'm doing this because I want this volume, the formula for the volume, to be in terms of H. Because they're telling me in this case here, let V be the volume of the water in the tank and let H be the depth of the water. You want to write an equation that relates V and H. I cannot have R in that equation. It has to be the volume, has to be in terms of H. So this is where those similar triangles are going to come in. So in this case here, the similar triangles is this. This side has a ratio of this side right here. The height relates to this height. 18 is to h, as the radius of the big one triangle is related to the radius of that triangle, 9 over r. Now, in this case here, I need to solve this equation for r, so that way, when I substitute it for the r in the formula for the volume, that formula for that volume will be in terms of h. Okay, so now cross multiply 18 times r, that will be 18r is equal to h times a 9, that'll be 9h. So I have 18r is equal to 9h. And if I divide both sides by 18 to solve for r, that will mean r is equal to 9h over 18. And if I simplify the 9 over 18, 9 goes into itself one time, 9 goes into 18 two times. So that means the r is going to be equal to h over 2. R is equal to h over 2. Now I'm going to take that r is equal to h over 2, and I'm going to substitute it for the r in that formula for the volume of the right circular cone. Okay, so now v is equal to 1/3 times pi times r. We found that out to be h over 2. And that's going to be squared times h. All right, now if I simplify this, this will be v is equal to 1/3 pi. Square the h over 2, this will be h squared over 4 times h. And this is like a 1 in front of the h squared. So if I do 1/3 times 1/4, that's going to be 1/12. So I have v is equal to 1/12 pi times h squared times h will be h cubed. So this is the formula for the volume of that cone that's only going to be in terms of h. So I need to pull this back up a bit so I can fill in my answers here. So this is v is equal to 1/12 pi times h cubed. Okay. And now I can differentiate both sides of the equation with respect to t. Okay, so in this case here, differentiating this in terms of t with respect to t, the left side would be dv dt, and that's equal to that 1/12 pi is a constant. I can bring that down. The derivative of h cubed would be 3h squared, and that's multiplied by dh dt. Now if I simplify this, this 3 goes into the 12 4 times. So dv dt is equal to 1/4 pi times h squared times dh dt. Okay, so now let's do some substitution here. All right, so we already figured this out that, well, we don't need r, that's that 9 feet. 9 feet, we're not going to need that. We do need the h, which is 5 feet. We do need to substitute dv dt, which is -3 feet per second square. 3 cubic feet per second. We're just finding out what dh dt is going to be. All right, so dv dt was that -3 feet per second, 3 cubic feet per second. And I'll just say -3. That's equal to 1/4 pi times the h was 5 feet. And if you want me to, I'll go ahead and write this out off to the side, where h is 5 feet dv dt was -3 cubic feet per second. And dh dt is what we're trying to find. And that h was 5 feet, so it'll be 5 squared. And then dh dt is what we're trying to find. Okay, so now let's simplify this a bit. Bring the -3 down. That's equal to 5 squared is 25. 25 times 1/4 will be 25/4 times pi times dh dt. Now to solve for dh dt, this is like 25 pi over 4. The reciprocal of 25 pi over 4 would be 4 over 25 pi. So I'm going to multiply both sides by 4 over 25 pi. Now, as you're going to see on the right side, the 4 will be gone. 25 pi would be gone. Now, if I multiply 4 over 25 pi times the -3, which is like -3 over 1, I'm going to have -12 over 25 pi. And that's equal to dh dt. Now, in this case here, they want this to the nearest hundredth. I'll bring this back down here to the nearest hundredth as needed. I'll just type this into the calculator and give you the decimal value to 2 decimal places. Now, the height is in feet. The time is in seconds. So it's got to be in feet per second, by the way. Let's see, -12 divided by 25. Now I'm going to do second and half for the pi. Let's see, I'm doing something wrong here because this does not look right. -12 divided by 25 pi. Okay. What happened was I entered this all wrong here. This should be -12. I need parentheses around the -12 divided by 25, close parentheses, and then second and the hat key. Okay, and it's still wrong. Okay. Let's try this, -12 divided by, and then put 25 pi in parentheses. There we go, we got the correct answer there. -0.15 if we were to round it off to 2 decimal places. Okay. Okay, so you want to make sure that 25 pi is in parentheses. Otherwise, you're going to get a wrong answer if you don't put it in parentheses. So -12 and then in parentheses 25 pi, if you do this in the calculator. So to answer that question, when the water depth is 5 feet, the rate of change of the water depth is going to be about, and let me pull this back up to fill in the answer, -0.15 feet per second. Okay. And I think I forgot to do something else here. That dv/dt, that's going to be 1/4 pi h squared times dh dt. So let me go ahead and fill that in as well. 1/4 pi times h squared dh dt. Okay. So as you can see here, this is a very long and complicated example I just gave you, where you have to use a concept of similar triangles here in order to do this particular related rate problem. And also you had to use similar triangles so that way you can write your formula for the volume in terms of a single variable. So here we have to solve for a expression in terms, with the radius equaling to something in terms of h. Okay. Okay, here's example 11. And that's this. Here we're dealing with a hemispherical tank with a radius of 9 meters and is filled from an inflow pipe at a rate of 3 cubic meters per minute, as you can see here. How fast is the water level rising when the water level is 7 meters from the bottom of the tank? Now here they're giving you a hint that the volume of a cap of thickness h sliced from a sphere of radius r is going to be this: pi times h squared times the quantity 3r minus h, and the whole thing is divided by 3. Okay, so let's identify what we already have first and go from there. This has to be the change in the volume because it's in cubic meters per minute. So that's dV dt. And we're told that the height of the water level is 7 meters from the bottom of the tank. So h is 7, that's in meters. And we're trying to find how fast is the water level rising. That's a change in the height, dH dt. Now we're told that we're going to let V be the volume of the water tank and let H be the depth of the water. Write the equation that relates volume and height, V and H. Okay, so let me do this. That formula that they give us, the volume of the cap of thickness H from a sphere of radius R, is that pi times h squared times 3r minus h. Oh, that's divided by 3. I know something else here. I see the radius here of this hemisphere, of this hemispherical tank. That's 9 meters. Let's use that by substituting this r with the 9. R is 9, so let's substitute that r with 9 in this formula for the volume. So that way it will be in terms of h. So it'd be pi times h squared multiplied by 3 times r, which is 9 minus h. Whole thing is divided by 3. Simplify this. This will be v is equal to pi times h squared times 3 times 9 is 27 minus h, all divided by 3. Distribute pi h squared over 27 minus h. This is what you'll get. V is equal to 27 pi times h squared minus pi times h squared times the h here in the parentheses will be h cubed. Oh, that's over 3. Now I'm going to divide each of these terms by 3. So this one I'm going to have 27 pi h squared divided by 3. Well, 27 divided by 3 will be 9. So it's 9 pi h squared minus pi h cubed would be over 3. So my volume is going to be in terms h, as you can see here. All right, so the equation that relates v and h, let me pull this down a bit so I can fill in the blank. That'd be v is equal to 9 pi times h squared minus pi h cubed over 3. Now we're going to differentiate both sides of the equation with respect to time. I'm going to do this on the right side. So this is what v is. I can find dv dt. Differentiate both sides with respect to time. Here I got 9 pi. I'm going to bring that down. The derivative of h will be 2h times dh dt. And then minus, at pi over 3, I'm going to bring that down. The derivative of h cubed is going to be 3h squared times dh dt as well. So now dv dt is this, and I apologize for scrunching all of this with a minimum amount of space on the paper that I have. So let's see, 9 pi times 2h, that would be 9 times 2, which is 18 pi times h dh dt minus, notice that these 3's divide out. I will have minus pi h squared times dh dt and if I factor out the dh dt, this is what I'll have, 18 pi h minus pi h squared. That'll be multiplied by dh dt. Okay, dh dt is the common factor in both of those terms. I'm just factoring out the dh dt to get this. All right, so in this case here, dv dt would be equal to, when we differentiate both sides, that's going to be equal to, I'm going to have to use a different pen since I can't get all that in there. Let's see, 18 pi h minus pi h squared. That's multiplied by the dh dt. So now let's use that to find when the water level is 7 meters from the bottom of the tank. The water level is rising at the rate about what? And let's use what we're given in this problem here. dv dt we know is 3 cubic meters per minute. That's given to us in that problem. So let's substitute dv dt with 3. That's equal to 18 pi times the height. The water level is 7 meters. That's your h. So it'll be 18 pi times 7 minus pi times h is 7 again, and that's squared, times dh dt. So I got 3 is equal to 18 pi times 7. Well, 18 times 7 is 126. So that'll be 126 pi minus 7 squared is 49 times pi would be 49 pi times dh dt. Subtract 49 pi from 126 pi, you'll get 77 pi. So it'll be 3 equaling to 77 pi times dh dt. And to solve for dh dt, we divide both sides by 77 pi. So now dh dt, and we're to round the answer to 3 decimal places in this case. So using the calculator, I'm gonna have 3 divided by and I'm going to put the denominator in parentheses, 77 second and the hat for the pi, close parentheses. That would be equal to, now the 3 decimal place, that would be 0.012. And this is, of course, in meters per minute, because our height is in meters. The time we're dealing with is in minutes. So in this case here, when the water level is 7 meters from the bottom of the tank, the water level is rising at a rate of 0.012 meters per minute. Okay. And finally, example 12. A hot air balloon is 160 feet above the ground when a motorcycle traveling in a straight line on a horizontal road passes directly beneath it, going 30 miles per hour or 44 feet per second. If the balloon rises vertically at a rate of 6 feet per second, what is the rate of change of the distance between the motorcycle and the balloon 6 seconds later? Okay, let's think about this. I know there's a hot air balloon that's going to be 160 feet above the ground. Okay. So let's say our hot air balloon is right here. And then you got a motorcycle traveling on a straight line on a horizontal road. So here's a motorcycle right here. Passes directly beneath it, going 30 miles per hour. So here we're trying to find the distance between the motorcycle and the balloon 6 seconds later. Okay. That means we want this distance between these two. Notice in this case, this forms a right triangle. Notice that it's forming a right triangle. So that means we need to use the Pythagorean theorem. And in this problem, they're telling you to let x be the horizontal distance from the balloon to the motorcycle. That's the horizontal distance. So this is what x is. And y be the vertical distance from the balloon to the road. Here's the road. There's a balloon up there. That distance is going to be a y. And z be the distance between the motorcycle and the balloon. Between the motorcycle and the balloon, that's your z. Write the equation relating x, y, and z. Well, we have to use the Pythagorean theorem. And of course, if you remember, the Pythagorean theorem is going to be that a squared plus b squared is equal to c squared. And here, this is x. I'm going to let a be the x, so it'll be x squared. B will be the y, that'll be y squared. C would be the z squared. So x squared plus y squared plus z squared, equal to z squared, equal to z squared. That's going to be my equation that I'll be using here. And in this case, I would go ahead and differentiate both sides of this equation in terms of with respect to time. Okay, so in this case here, this is x squared plus y squared is equal to z squared. The derivative of x squared with respect to time would be 2x dx dt, plus the derivative of y squared with respect to time, that'd be 2y dy dt, equaling to the derivative of z squared with respect to time, 2z dz dt. So that's 2x dx dt plus 2y dy dt plus 2z, equal to 2z to dz dt. All right, so now let's look at what we are given in this particular problem here. Okay, now I need to pull this paper down a bit or just lift this up if I can. Okay. Let's see here. The hot air balloon is 160 feet above the ground. That doesn't tell me much of anything. And of course here, passing directly at 30 miles per hour or 44 feet per second. Well, that tells me this. You have a motorcycle traveling in a straight line on a horizontal road, passing directly beneath the balloon, going 30 miles per hour or 44 feet per second. That's this distance right here. It's going at a rate of 44 feet per second. That would be dx dt, if you look at it. So dx dt would be 44 feet per second. The balloon is rising vertically at a rate of 6 feet per second. So there's a change in y, so that's dy dt. Six feet per second. And then we want the rate of change of the distance between the motorcycle and the balloon 6 seconds later. So we're looking for dz dt. So I'm putting a question mark there. All right, 6 seconds later. That means that your time is 6 seconds. I need to find out what the distance is for the motorcycle and the distance for the balloon 6 seconds later. Okay, let's start with the distance for the motorcycle, which is your x. Now, to find the distance, there is a formula for finding the distance of anything when you're given a rate and a time. Okay, so that x will be equal to r times t. If you remember the formula, distance is equal to d is equal to r times t. D is the distance, r is the rate, and t is the time. If you know the rate and you know the time that you traveled, you can always find the distance. That's what we're going to use here. T is 6 seconds, so we know that the motorcycle is traveling at 44 feet per second. So if I take that 44 feet, which is the rate, the time is 6 seconds. 44 times 6 will give me 264. So the distance of that motorcycle is 264 feet. That's what x is. Now I need to find the distance that the balloon has traveled. Okay, so let me pull this paper up. Y is going to be the distance of the balloon, which is also going to be rate times time as well. So I'll say y is equal to rate times the time. Now here, the rate that the balloon is traveling is 6 feet per second. So that's going to be 6 times the time, which was 6 seconds. That would be 36. But that's not actually what y is going to be. Because if you look at it, that hot air balloon is already 160 feet above the ground. So we need to add that 36 to the 160. Okay, so this will be plus 160. And I might as well do this on the next line right here. That's 6 times 6. And then we add 160 to it. So this will be 36 times 160, which makes that 196. So the height of that balloon 6 seconds later, that's 196 feet. Okay. All right. Now we know what y is, we know what x is. We can find out what z is using that Pythagorean relationship, where we got that x squared plus that y squared is equal to z squared. Let's use that to find out what z is. Okay. So x is 264 feet, so it'll be 264, and that's squared, plus the y, which is 196, and that's going to be squared, is equal to z squared. So now if I square the 264, that's going to be 69,696. Plus square the 196, you're going to get 38,416. That's equal to z squared. Now add 69,696 to 38,416. We'll get 108,112. And that's equal to z squared. And for z, we're going to get a decimal, so I'm going to leave this as the square root of 108,112. So this is the length of z, the square root of 108,112, and that's in feet, by the way. All right, next is this. Since we know what z is, and x and y, and we know what dy dt is and dx dt is, we can use that formula where we differentiate the equation where we differentiated both sides, which is that 2x dx dt plus 2y dy dt equaling to 2z dz dt. And in this case, we just do our substitution here. This will be 2 times x, which is 264, times dx dt, which is 44, plus 2y, or 2 times the y is at 196, times dy dt was 6 feet per second. I'll just substitute that with 6, equaling to 2z. 2 times z was the square root of 108,112. And dz dt is what we're finding here. Because we're told to find the rate of change of the distance between the motorcycle and the balloon 6 seconds later. Okay, So now let's simplify this. If I do 2 times 264 times 44, I'm going to end up with 23,232 plus 2 times 196 times 6 would be 2,352 equaling to, and in this case here, I'm not going to simplify the right side. This will be 2 times the square root of 108,112 times dz dt. Now, if I add these two numbers together, the 23,232 and the 2,352, I get 25,584. That equals 2 times the square root of 108,112 dz dt. And then we'll divide both sides by 2 square root of 108,112. So dz dt, and by the way, those are z's, by the way, dz dt. Okay, now they say to 2 decimal places, so we have to do this in the calculator. This will be 23,584 divided by left parentheses 2 times, and then second square root 108,112. I'm going to use my right arrow key to get out of the radical, close the parentheses, hit enter. Okay, I made a mistake. When I added these two, this should be 25,584. So I just changed that 23,584 to 25,584. There we go. To 2 decimal places, that would be 3.38.90. And this is going to have to be in, the Z is in feet, the time is in seconds. Feet per second. So to answer this question, the rate of change of the distance between the motorcycle and the balloon after 6 seconds is about 38.90 feet per second. So that's the answer that they're looking for. So this is going to be 38.90 and then feet per second. Okay. So as you can see, that is a lot to deal with in this case. It's all a matter about reading the problem carefully, identifying the bits and pieces that are in that problem. Once you're able to do that, you should be able to go ahead and try to find those rates here. And also, you have to be familiar with the formulas that are used for those geometric figures, and also be familiar with the Pythagorean Theorem. Okay, because this one, you have to use the Pythagorean Theorem. Okay, and also you have to know that the distance is going to be rate times time. Okay, so that concludes this video on section 3.11, dealing with related rates. Feel free to contact me, or stop by my office if you have any questions about anything that is related to what's presented in this video or any of the homework problems in my math lab. Okay,